Welcome to the University of Nottingham podcast.
The University of Nottingham is leading 2 of 6 research projects being run by the national £27 million BBSRC Sustainable Bioenergy Centre. It was announced today in London. This will be the biggest ever single UK public investment in bioenergy research. Now, experts in microbiology and brewing science at the University of Nottingham will be leading the 2 5-year research programmes, but don't just take my word for it.
The component of the research in my programme is actually all about converting plant materials. Those are plant materials that have come from the inedible components of plants. So we're talking about things like the leaves from the tops of various fruits. To give an example, the top of a pineapple, the leaves and stalks from all sorts of different vegetables, including tomatoes, grapes. And what we're going to be doing with that kind of material is finding ways to unlock the sugars that are in those waste materials. When we've done that, we'll be converting those sugars into ethanol using yeast fermentations. It's hugely important for 2 reasons. First of all, it's very important for us to find real potential for our waste materials. We dispose of a lot of items that actually contain some very important energy, and what we want to do is kind of capture that energy and convert it into a really usable form. The fermentation to ethanol is very important because the ethanol product that we make can be used to blend with petrol, and it will prolong our fossil fuels as a consequence, but also eventually it will be a replacement for fossil fuels. Some of my existing research has concentrated on fermentation and really optimising fermentation. When you're producing alcoholic beverages, for example, it's actually also about flavour development as well. But the brewing and distilling processes generate some wastes, things like spent yeast, which is the yeast that's been used in the fermentations, and we can use that to produce all sorts of different products. Including animal feeds. We can also use it to produce base chemicals for the pharmaceutical industry, and so this is an area of real interest for us in our research. I'm very excited. This is a unique opportunity to work with the best talent in the UK in engineering, chemistry, even in social sciences, because we're going to be considering the social impacts of some of the technologies that we produce, so that we make sure that we produce sustainable products for the fuel industry. And also working with companies as well that either will be producing fuel in the future or are actually generating some potential waste materials that we can utilise as part of their processes. So it's hugely exciting for everybody involved in the consortium. We can't wait to get started.
The clear distinction between what we're doing here within this energy centre is that we are focusing on growing our organisms on waste plant material or specific energy crops, so that we don't have competition with food crops. And in order to achieve that, we have to be able to break down cellulose, which is the major component of plant cell material. And so the sugar that the organisms need to convert into biofuel are locked up within this very complex substrate. And so what we need to do, and what many of the other programs are doing within the centre, is coming up with more effective ways of degrading that cellulose. But it turns out that Clostridia are a very ancient genus, and they evolved on this planet long before there was an atmosphere. And because organisms that don't have access to oxygen can't grow so efficiently, they have to derive much more efficient processes for degrading substrates. And so it turns out that Clostridia have one of the most effective systems known for degrading cellulose. So what we also want to do is select and breed strains which not only make butanol but also very efficient in degrading cellulose. And then we'll be able to grow the organism directly on waste plant material. Butanol has significantly improved properties over ethanol. I mean, I would look on it as a supercharged ethanol, if you like. So it gives greater energy, it gives greater fuel economy. It can be used in engines up to much higher percentages than ethanol. So ethanol can only be blended up to about 10% without having to modify the engines. With butanol you can blend at much higher levels, and in fact you can run engines on 100% butanol if necessary. And another significant factor is that it's very easy to transport, so you can actually pass it down the same pipelines we currently use for petrol. Now you can't do that with ethanol, you have to transport it in tankers or on barges or in trucks. And furthermore, it has potential to be used in aviation fuel, which again ethanol can't be used in aviation fuel. So there are significant advantages over butanol. The organism that makes butanol, it also makes other chemicals as well. It makes a bit of ethanol and it also makes acetone. And in fact, that's when the organism first came to fame. It was used during the First World War to make acetone, which was then used to make cordite. And in fact, the acetone-butanol process, as it was called, was the second only importance to ethanol up until about 1960. And it was at that stage that the use of petrochemicals really took off and it became uneconomic to run the process. So really, I just think we're almost returning to our roots in going back to these biological processes. I firmly believe with the tools that we have available to us that we will make significant progress within the 5 years. At the moment, the organism doesn't produce enough butanol and it produces these unwanted byproducts of acetone and ethanol. And really what we need to do is select and breed strains that produce only butanol and at higher levels. And I'm convinced that is easily doable within the first 5 years of this programme.